In the last video, I talked a lot about what is an Euler path and Euler circuit. In this one, I wanted to talk about how do we find them and how do we know. And just to return back to summarize what the information synthesized from Euler's theorem is in order to determine whether a graph has an Euler circuit or Euler path, we need to count the number of odd vertices in the graph. Because the answer to, well, does it have a circular path, really is predicated on exactly that. And just to review, if it has 0 odds, it has an Euler circuit. If it has 2 odds, it has an Euler path. If it has more, so I'm going to go ahead and write this would mean Euler circuit. This would mean Euler path. And more means it would have neither an Euler circuit nor an Euler path in that graph. And actually, I did mention technically it's impossible to have one. And actually, I forgot to mention some of Euler's other theorems as well, which are on the next slide, but we'll get to that in a minute. So what we'll do is let's practice determining whether these following graphs have Euler circuits or paths. And if you want, you can pause it right here and try for yourself to determine what case we're dealing with. So looking at this first graph, what we would do is figure out, well, are there any odd vertices and label them? And what I like to do is circle them all just so I can get a visualization of how many odds I have and where are they. And looking at this graph, another helpful way you can remember it is corners and like larger cross intersections are degree even because it's 2 and 4, but T intersections like this, like capital T, technically this is a T2, but usually when people refer to a T intersection, it's degree 3, like this. T intersections are degree 3, and those are helpful things to look for in a typical street setup for even and oddness. And if we return back to the very, very first problem, if we look at this, notice that if we're trying to figure out whether this has an Euler circuit or path, notice how many T intersections were along this graph, and why it's impossible for there to be an Euler circuit. And if you remember when I was struggling or when I was explaining the problem with trying to solve the street routing problem here and the need for deadheading, especially when going down these blocks back and forth, if we're thinking about it now, really all of those odd vertices were the problem issues because since they were odd, we had to deadhead. And notice that really in a real street setup, there tends to be many, many odd vertices. But anyways, looking at some of these sample graphs, in this graph, well, each of those corners are 2. So 2, 2, 2, 2, 2, 2. Up here, notice that a setup like this would typically would be odd, but actually since there are multiple edges, technically this one has a degree of 4, as does this. So those two are both also even. And actually looking at this one, typically this would be degree 4, but since there was an extra edge, this is actually 1, 2, 3, 4, 5. So this graph has actually 2 odd vertices, which means that this one would have an Euler path. This graph would have an Euler path instead of an Euler circuit or neither. Since if it has exactly 2 odd vertices, it has at least one Euler path. And note that if I was trying to actually find the Euler path, which we will practice soon, it has to start at one and end at the other. And looking at the next graph, actually notice that this graph looks a little bit strange, and you might be wondering, okay, what the heck is going on with this thing here? But I wanted to mention a strange look to it. It's just this is a way that some people will draw a graph, which is specific to a particular meaning. And really, it's kind of like if you think about in the real world on a map when sometimes you have a street with another street that goes over it, right? So while their streets are really, if from an overhead map perspective, it looks like they're connected in their intersection, they really they're not really crossing. So in graph theory, how we typically would write that is it would be kind of like this, where we have overlapping edges, but there is no vertex there. So when we're writing this, technically the lines appear to overlap, but since there is not a vertex, what this means is that those lines are not overlapping. So if we were to put a vertex there, that would mean something different. That means you can turn there, whereas this means you cannot. And it's an important distinction. And you might have been wondering that back when we were looking at this example right here, because there was no vertex in the middle. So what was going on there? But again, technically these lines are not adjacent because they're not connected and there is no vertex there. And these would not be separate lines. This would be all one singular edge. There would not be two separate edges connecting there. But if I was to put a dot there, I would call that, say, for example, E. That would be something different. And it would be a different graph. But so going back to this, what is the deal with this thing? Well, sometimes how people write this or draw it on a map setup would look instead like this. Because let's say I have a bridge over another road. A lot of times people draw it kind of like this, where you have like a tunnel or something, which would be a more of a different representation. But instead of actually drawing a tunnel, sometimes you will see graphs. This is not really technically correct for graph theory, so you really shouldn't do this yourself, but I just wanted to mention how some people actually will draw it like this. And what that really means is the same thing, where you have one bridge on top of another. And again, technically it's not the graph theory term bridge, which is why, you got to pay attention to what the terms mean in graph theory, not necessarily the same as the real world term. But like as a tunnel situation, occasionally you will see a graph drawn like that. And that's why I wanted to show you this one. Anyways, that's what this weird thing means. It's not really like two dead ends. So I'm not going to give you these sort of examples on tests because it's really not proper at the end of the day. But you can kind of use some common sense as you're dealing with this. Anyways, so back to the initial question, it said determine whether these graphs had Euler circuits, paths, or neithers. But again, it had to do with the number of odds. So what I want to first do is, well, identify the odds and count them all up. So here there was an odd vertex there and there. It looks like those are the only two, and the rest are either degree 2 or 4. So this one as well would have an Euler path because it has exactly 2 odds. This third graph has an odd here and here. Again, would have an Euler path exactly 2. So far, all of these examples have Euler paths. I think the other ones are different. Looking at this graph, notice this is 2, 2, 4, 2, 2, 2. This one has 0 odds, so this one would have an Euler circuit instead. Again, and this is all due to the same reason, Euler's circuit and path theorem, which basically I've summarized here. And looking at the last graph, this one we've already found the odds previously, which would be here, 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 and here. So this one had a total of 6 odds, and in those cases, the graph will have neither an Euler path nor Euler circuit, meaning it's kind of like it's too complicated. There's too many stopping points to actually be complete. And this is how we find whether or not graphs have Euler's paths or circuits. In the next video, we will talk about why, and we'll look at how you actually find the paths and circuits from scratch.